What if you woke up one day and all digital devices in your life ceased to work? Picture that for a moment. No smartphone buzzing with messages, no laptop humming with data, no digital appliances making your life easier. It's almost unimaginable, isn't it? That's because we're living in a world where digital electronics is deeply woven into the fabric of our everyday lives. From the smartphones in our pockets, the computers on our desks, to the appliances in our homes and the transportation systems we rely on, they all operate on the principles of digital electronics. This fascinating branch of electronics uses discrete signals, typically zeros and ones, to represent information, unlike its analog counterpart that uses continuous signals. It's the language of our modern technology, the code running our world. With digital electronics underlying modern technology, understanding its key concepts is crucial. At the heart of digital electronics are digital signals with their binary language and logic gates. Digital signals are the messengers of the digital realm. Unlike their analog counterparts, which convey information through a continuous stream of data, digital signals deal in absolutes. They are discrete, taking on specific values, typically 0 or 1, and nothing in between. This binary language is the lingua franca of digital systems, with each 0 or 1 being a binary digit, or bit. Each bit represents the smallest chunk of data, a fundamental unit of information in the digital world. Imagine digital signals as couriers, zipping between components within a digital system, carrying packages of bits. Each package, whether it's crammed with zeros, ones, or a mix of both, conveys a specific piece of information. This could be a simple on or off command, a complex mathematical value, or anything in between. But what's the use of these couriers if there's no one to send or receive their packages? Enter logic gates, the diligent workers of the digital realm. These are the fundamental building blocks of digital circuits, tasked with performing basic logical operations. Whether it's an AND, OR, NOT, NAND, NOR, or XOR gate, each has a specific job role in the grand scheme of digital logic. They take in binary inputs, process them according to their designated operation, and produce an output. Consider a simple AND gate. It's a binary decision maker. If it receives 2 ones, it outputs 1. In all other cases, it outputs 0. It's like a strict bouncer at a club, only letting in a pair if both are dressed in ones. By stringing together these logic gates, we can create complex digital circuits capable of performing intricate computations, all based on this simple binary language. From the simplest calculator to the most powerful supercomputer, they all rely on the harmonious dance of digital signals and logic gates. So digital signals and logic gates form the bedrock of digital circuits, making complex computations possible with simple binary language. Now let's delve into the binary number system and the memory components that hold this binary information. The binary number system, or base 2, is the beating heart of digital electronics. Unlike our familiar decimal system, which uses 10 digits, binary only uses 2, 0 and 1. Every number, no matter how large or small, can be expressed using just these 2 digits. This is the language of digital systems, a language that can be understood and processed efficiently by electronic circuits. One might ask, why binary? The answer lies in the simplicity and reliability of representing and processing 2 distinct states. By using high and low voltage levels, for instance, we can easily depict zeros and ones. This binary data, or bits, is the fundamental unit of information in digital systems. Now, where do we store these bits? Enter flip-flops, the basic memory elements in digital systems. A flip-flop is capable of storing a single bit of binary data, either 0 or 1. It's like a tiny electronic box that can hold a bit, and remember it, even if the power is turned off. However, a single bit of information isn't usually enough. We often need to store larger chunks of data. This is where registers come in. A register is essentially a group of flip-flops, working together to store multiple bits of data. For even larger data storage, we have memory units, such as random access memory, RAM, and read-only memory, ROM. These are like vast libraries filled with registers that can hold vast amounts of data. RAM is like the working desk of a computer, holding data that is actively being used, while ROM is more of a reference book, storing data that doesn't change. The magic of digital systems comes from the ability to store and manipulate binary data. From simple calculations to rendering complex graphics, it all boils down to a series of zeros and ones, stored and processed within these memory components. From binary numbers to memory storage, the ability to store and manipulate information is what makes digital systems so powerful. Moving forward, let's explore the brains behind our digital devices, microprocessors and microcontrollers, and the fascinating world of digital signal processing. Microprocessors, often referred to as the heart or the brain of a computer, are central processing units that carry out instructions of a computer program. They perform fundamental operations such as arithmetic, logical, control and input-output operations specified by these instructions. Each advancement in microprocessor technology has brought us faster and more powerful computers, enabling a world where technology continues to expand and evolve at an unprecedented pace. On the other hand, microcontrollers are like mini-computers on a single integrated circuit. They contain a processor core, memory, and programmable input-output peripherals. Microcontrollers are often found in products that require a degree of control to be exerted by the user or the environment. These include home appliances, automobiles, toys, and other embedded systems. In essence, they are the tiny brains that inhabit many of the devices we use daily. Now, let's delve into digital signal processing, or DSP. It's a method of analyzing and modifying signals to improve their quality or optimize them for a specific purpose. DSP plays a crucial role in a variety of applications. For example, it's used in audio processing to reduce noise, enhance clarity, or create special effects. In image processing, it can help sharpen blurry images or enable facial recognition. And in telecommunications, it's responsible for compressing data for faster transmission and then decompressing it upon reception. So, whether you're scrolling through your smartphone, adjusting the temperature on your smart thermostat, or listening to your favorite podcast, you're interacting with the sophisticated world of microprocessors, microcontrollers, and digital signal processing. These components and processes are what enable our devices to compute, communicate, and interact with the world. Lastly, we'll touch on some advanced concepts that make the digital world even more versatile. Programmable logic devices, or PLDs, like field programmable gate arrays and complex programmable logic devices, can be programmed to implement digital circuits. This flexibility allows us to design and tailor our digital systems to a wide variety of applications. Then we have multiplexers and demultiplexers. In simple terms, a multiplexer combines multiple input signals into a single output, whereas a demultiplexer does the reverse, directing one input signal to one of several outputs. These components are essential for managing the flow of information in a digital system. In the realm of digital communication, systems transmit and receive information using digital signals. Through modulation and demodulation techniques, digital signals are converted into analog signals for transmission and back, allowing for efficient and reliable communication. Clocks and timing play a crucial role in coordinating the operation of various components in a digital system. The clock signal provides a timing reference, ensuring that all parts of the system work in harmony. Moving on, we have sequential and combinational logic. Combinational logic circuits perform operations solely based on input values. In contrast, sequential logic circuits incorporate memory elements and their operations are influenced by previous states. VHDL and Verilog are hardware description languages used for designing and simulating digital circuits. These languages allow us to describe and test our digital designs in a structured and systematic way. Lastly, let's talk about digital design principles. These include Boolean algebra, Carnot maps, and state machines. These principles form the foundation for the design and analysis of digital circuits, helping us to create efficient and reliable digital systems. With these concepts, digital electronics pushes the boundaries of what's possible, shaping our world in ways we could only dream of. So that's a whirlwind tour of digital electronics. Quite a journey, isn't it? We've delved into the core concepts and components that make up this fascinating field. From the basic building blocks of digital signals and logic gates to the binary number system that forms the basis of all digital systems. We've explored memory components like flip-flops, registers, and the indispensable RAM and ROM. From there, we ventured into the realm of microprocessors, microcontrollers, and digital signal processing. We've touched upon advanced concepts including programmable logic devices, digital communication, and the critical role of timing in synchronous digital systems. And let's not forget the design principles that guide the creation of these impressive digital circuits. All these elements come together to form the digital world that surrounds us and continues to shape our future. Remember, the world of digital electronics is vast and always evolving, so keep exploring, keep learning, and who knows where your understanding might lead you.